Hello, and welcome to our presentation, How Marvel Strike Force Transitioned to URP. We will dive into how we did this transition from research to release and how we converted existing assets using custom tools. I'm Emily Wittkowske, the graphics engineer on Marvel Strike Force.
Hello, I'm Aguirre, Samaniego, the lead technical artist on Marvel Strike Force. There's a picture of me in case you're wondering what I look like.
So we will go through how we decided to migrate to URP and why that would be beneficial to our project, how we handled the migration process, and what we learned from this process and what benefits we gained. So we decided to migrate to URP because we knew that our original pipeline was hindering development and needed to be improved. We evaluated the costs and benefits of improving our original pipeline versus migrating to URP. Our original pipeline is designed for devices we no longer support. It was necessary and beneficial in the past, but it doesn't provide what we need to continue developing for new and upcoming devices. It carries significant complexity that was meant to scale all the way down to the iPhone 4, but we'd already deprecated a lot of this support by the time we released the game back in 2018. The pipeline meant to scale up to new and upcoming devices through the support of deferred rendering, but this didn't emerge as a great fit for our game, so we'd only been supporting it in the context of marketing captures. And achieving physically based rendering of the target quality at the time Marvel Strike Force was released required the use of a custom content pipeline. However, this pipeline hasn't been actively maintained or expanded since, yet blocks use of newly developed and improved Unity tools, frameworks, things like that. Our original content pipeline involves the generation of optimized and baked copies of source assets, including models, textures, shaders, prefabs. Many such copies have diverged from their source in either specific feature support or something like that over the years. In addition, the project has grown to a point where we can neither recreate all of our baked assets from source, nor can we effectively propagate changes to generated assets in bulk.
Oh my God, our scene view. I could genuinely give an hour-long presentation on this. This is what we actually had to work with for about 5 to 6 years since our project has launched. And the thing about Unity is what you see is what you get. You should be able to iterate in the scene view and get a proper game view at the same time. And unfortunately, it's using the wrong render, the lighting doesn't work, there's all kinds of sorting issues. So navigating in the scene view to actually diagnose issues or hand place assets is actually needlessly complicated in our current pipeline, or our old pipeline now. And we just ported things over to URP and immediately noticed a shocking revelation that we can have our cake and eat it too. So we can actually have a working scene view. One of the big reasons that we wanted to move to URP as well is huge iteration time to just select things and hand place things. You would literally navigate with the camera with this broken view, by the way, select something, and there would be like 10 other things in front of you before you actually get what you want, which can add significant delays to really solving your problems and putting in new content.
For these reasons, we decided that updating our existing pipeline wouldn't be an effective use of our time, and switching to URP would provide superior long-term benefits. So we developed a migration plan to ensure that we could achieve visual parity and convert a large number of assets efficiently. We began the migration process by investigating URP to plan out how we would migrate the features from our original content pipeline into URP. We implemented these features and manually converted a few assets to create a proof of concept. We used the learnings from our proof of concept to create custom asset conversion tools. In order to create the proof of concept, we needed URP versions of our original shaders from the original pipeline. The standard URP shaders didn't provide all of the functionality that we needed. So we migrated the functionality from the original pipeline to custom shaders in URP. We created custom versions of the URP lit shaders, as well as included HLSL files such as lit input. We added additional properties and modified calculations to support our custom version of these shaders. Support for composite textures was one of the features that we migrated over. Many of our assets use composite textures that combine smoothness, metallic, emissive, and ambient occlusion texture maps into a single texture. We use two main versions of these. One is just smoothness, metallic, and ambient inclusion, SMAO, and one is with the emissive texture, so SMEAO. We added the composite texture as a 2D property and a shader feature to support both of those variants. We created a custom editor inspector for the shader using extending Unity's shader GUI class. When the composite mode is changed, the custom editor inspector updates the material keywords to reflect the selected mode. So in the example, Captain America uses an SMAO mode. So having that selected enables the SMAO keyword on the material. In addition, we modified our custom version of the lit input HLSL to sample the composite texture and extract values for properties in the texture in the initialize standard lit surface data function. We assign these values to the corresponding variable in the surface data struct. These modifications allowed the composite textures to work the same as in our original pipeline. Once we had the necessary features implemented, we manually converted a representative handful of assets to verify that we could achieve visual parity or better.
So here for our proof of concepts, we needed to prove a few things before we transitioned to URP, which can we achieve visual parity or better? Can we reduce our iteration time for creating new content and even integrating it as well? And also expose what pipelines we currently have that need to be ripped out and replaced. So here you can see a before image of what we were dealing with. There's poor lighting. Mysterio really doesn't have any detail to him. And when we ported it over to URP, we noticed significant increase in detail, fidelity, lighting quality, etc. And as far as other things we had exposed was our composite texture workflow was created in the engine. So those textures Emily was talking about in the previous slide, it was done through a process called merging, which would create those composites internally. And that process was removed from the artists themselves. And that process is done for every character. It takes about 6 to 10 minutes to set up a character prefab doing this process. Multiply this times 300 characters over 6 years. It's a long time that we have spent basically needlessly doing something this long and repetitive. So now that we've removed that process was basically, we created a new pipeline for that for the artists themselves to export that composite texture through the chosen software of their choice. So Substance Designer, for example. So now they have creative control over their textures. They don't have to compromise on certain maps to cater to the old engine anymore. So any of the old flaws that they would have to introduce artificially to look correct in the old engine are no longer the case. It's now true PBR. What you see in one software, it's going to be exactly the same in the other software. This iteration time also reduced, probably took like 5 minutes out of the whole process for integrating a character on our pipeline, which is pretty big, as we're constantly churning out new characters every release. It can be like every 4 to 6 months. Not only that, but again, I mentioned true PBR, like what you see is what you get with all those types of textures. Like when you integrate a full PBR texture set, it should look like what it looks like in Substance Painter and in the engine as well. And this is the actual original author intent of how Mysterio should look. Over here is what he actually looked like for many years for us. And the artist who originally created him was a little bummed out that, that's going to be on this portfolio, but now it's displayed properly. So that was a huge benefit for us from moving to URP in our proof of concept. We did the same thing with environments. We needed to prove, one, can we achieve parity or better? Can we reduce iteration time? And more importantly, our old content pipeline for environments was broken. We had resurrected it, but it's still based on an old archaic pipeline that's, it's outdated, and the knowledge for it has been lost over time. Documentation hasn't been kept up to date, and maintaining it only really just proved to cause more issues than it did solutions. You fix one thing, 10 things break down the line. So in URP, we said, well, let's convert it first and can we achieve parity? And we got parity and better. One thing you can notice right away, this is all baked lighting and the characters are artificially lit, but there's like shadows, but there's no directional light. So it's kind of weird. You can't actually see a light in our old pipeline. It's a little strange. But over in URP, that's all dynamic. It's not artificial anymore. There's an actual directional light for the environment. There's some baked lighting here as well, but the characters also have their own unique custom light for our proof of concept, something we didn't really have before. So it's no longer artificial. It's actual real-time lighting mixed with fake lighting as well, which luckily Unity can support that with mixed fake lighting. Also, something we had to prove was iteration time for baking. It used to take 30 minutes or an hour to bake an environment. And if you had to move a light 2 inches to the left, you couldn't stop that process, and it would stop. You wouldn't be able to use Unity during this process either. So if you made a mistake and you caught it too late, it sucks. You got to wait 30 minutes, move it, and then wait another 30 minutes or an hour. With URP, it took 10 to 30 seconds to create a bake. And what's cool is I could move all the lights 2 inches to the left if I wanted to. Unity would just stop and rebake right then and there. Literally huge time savings for us when we plan to create new environments.
Manually converting assets for the proof of concept was error-prone and time-consuming. We needed an efficient way to convert existing assets as well as new characters and features in development. So we created custom asset conversion tools to automate as much of this process as possible. The goal of the asset conversion tools was to get about 90% accuracy so that artists could achieve the desired look with minimal polish work. And this allowed engineering to work in parallel and work on other parts of the migration process while art was polishing these assets. The tools converted combat scenes as well as prefabs. For combat scenes, we needed to convert materials, lights, and post-processing settings. For character and VFX prefabs, we just needed to convert materials and lights for the most part. Prefabs could be converted individually or in bulk. While we were developing the tools, we tested them on a variety of assets to verify accuracy and then make adjustments as needed. To convert the materials, the tools created a new material with a URP shader, transferred properties, and toggled keywords. The asset conversion tools converted custom values for our lights. We used custom lights in our previous pipeline. So it converted these custom values into URP light intensity and range values. For post-processing, tools converted values for the bloom and tone mapping into volume overrides in URP. Later on, we realized that a few of the assets weren't converted quite right, but it wasn't a big deal. Once we identified the issue, we were able to update the conversion tools to bulk fix any of the assets that we realized needed adjustments. So while we were doing the asset conversion tools, we realized that the shadows didn't quite look the same in URP as they did in our original pipeline. We tried modifying a few of the properties, such as the cascade split positions, but we just weren't able to achieve parity there. So we had a custom implementation for shadows in our previous pipeline, and we decided to migrate that to URP. In order to do this, we had to create a custom version of the URP package and modify source code. So we updated the shadow utils file to support custom view matrices, projection matrices, and cascade split positions. And with those modifications, we were able to achieve the same visual target. We have a script in each combat scene that manages the shadow settings as well as other scene-based settings. In the script, we use the begin context rendering delegate in the Render Pipeline Manager API to set up these values. We also use custom render passes to implement our warp and gradient effects. We tried out a few different implementations before finding the optimal solution. We found that the scriptable render features are better for render passes that need to be enqueued all of the time rather than just in specific scenarios. We found that injecting the render pass via script allowed us to efficiently manage resources used by the feature, such as render textures. These effects are only used in combat scenes. The warp effect is used for certain character abilities and background props, and the gradient effect is used to dim the background during storytelling. Both of these effects require additional render textures. So at first we used the scriptable render feature to enqueue the custom render pass, but when we did memory profiling, we found that those render textures were still present in memory even when the effect was disabled outside of combat. And we wanted to get rid of this render texture when the feature isn't enabled. We don't need to keep it around. There's no reason for that. So we tried another implementation, and we created two versions of our forward renderer. So we had one for combat and one for menus. So we attached the renderer features to the forward renderer for combat and assigned that as the renderer to all the cameras in combat. And then we had the one in menus, which didn't have the renderer features attached to it, and we assigned that to all of the menus cameras. But when we did memory profiling with this, we found that even outside of combat, we still saw those render textures in memory, which just wasn't what we wanted. So finally, we tried injecting the render passes via script, and this worked really well. We added a custom script to the camera in combat, and we were able to create and inject the passes when the features are enabled, and when they're disabled, we release the render textures. And when we did memory profiling with this, we saw our textures properly released when the effects were disabled, which was awesome. In addition, the warp effect also requires the use of a depth texture. There are settings on the URP asset for opaque and depth textures, so you can enable it there. But that will cause the pipeline to always generate these textures, which isn't efficient if you're not using them all the time. So for us, we just don't need them in the menu scenes whatsoever. We don't have those effects enabled. We just need them in combat. Fortunately, there are overrides on the cameras. So we just enable the override on the camera for the depth texture when we're actually rendering the effect. And then that way the depth texture only gets created when the effect is actually enabled. And then it gets released when we disable the effect.
What's cool about what Emily was talking about as well is it touches on VFX. And something we didn't really have before was the ability to debug and really do optimization passes on our VFX, other than the standard stuff of just watch your emitter counts, don't have too many of something, compress your textures, etc. But now we have tools like the render debugger, the frame debugger, and stuff like that, that we can actually use and see how many draw calls things are. Stuff that in our old pipeline just wasn't really working because it was so bespoke and so broken over the years. And we got some cooler things out of transitioning to URP too on the visual side, which was our VFX just got a huge boost in quality. Specifically, brightness was one of the things our artists really noticed. Things just look significantly brighter, way hotter than they used to be. And I can give you a quick preview, but I do warn this slide is a little bit bright, so sorry. Here's just a quick preview of Cyclops launching one of his beams. And here, with the combination of post-processing tools that we didn't have before, we have a new level of control of how intense our bloom is. And not only that, but that combined with our emissive values really gives us fine-tuning control to give characters their own unique levels of brightness, their own ways to stand out. Marvel has a lot of huge library of characters, so you can imagine a lot of them shoot beams. So to differentiate one person's beams from another can be challenging. So it's nice when you can separate the beams from like the ultimates or to the basics to make one brighter than the other, and then have some variety as well across a huge wide range of characters. And we got to talk about some of the visual improvements that we got from URP as well. And when we converted, we were aiming for visual parity and, iteration time, etc. But while we were there, we wanted to talk about like, what can we do to improve on the old? And as you can see here, there's quite a bit to talk about. So first things first is the lighting. We now have a 2-point lighting system that we established, something that we weren't able to do before because it was all artificial. And the cool thing is every character, Emily graciously developed a great component that we can attach to every character prefab. And that component, an artist can come in and say, hey, this light right here, make it purple, this one make it green, make the intensity 4 or 5, move the position over here. And this allows us to really highlight the character's best features. It allows an artist to really showcase their character in their best possible light. And the players get the benefit of seeing our characters in a completely new look and feel, which is awesome. I mean, just look at the difference in quality there. Another thing that we did for visual improvements is we got to take a look at some of our old assets as well. A lot of our characters are stuck in 2D UI and screens, and they're not really in 3D environments when you're looking at them through roster views and stuff like that, navigating our UI. So we could actually create different reflection probes for various environments and actually have those reflect what the UI is showing. And we've actually done that here with him. Before we were using like a default Unity sky, and that was just a limitation of the old system. Plus we never really updated it because it did break a few things. Now that that was no longer an issue, we were able to create a new reflection probe, give the characters and a new look and feel, make them feel like they actually belong in the screens that you're viewing them in. Another thing is we were able to actually take a look at the older assets from when we initially launched and also clean those up a bit as well. So during our conversion process, we were able to just kind of make things run a little bit more efficiently. And also the iteration time, again, to get to from creation of the character into the engine took less than 5 minutes for us. Before it would take significantly longer to go through that merge process, the composite and everything. Now it's just as simple as drag and drop and the character is visible and viewable. For our environments, same kind of story. We just, after conversion, we started talking about what can we do to visually improve on the old stuff. As you can see, there's a dynamic light that didn't exist before. It's now actually lighting the environment. So you can really immerse the characters in this environment, make it feel like they're part of being actually fighting on the rooftop and being lit by this helicopter spotlight. We were able to revisit old textures, old VFX, kind of plus them up just a little bit, give the game a new lease on life, essentially. Put lights where they didn't exist before. So now there's like, I don't think it's in this screenshot, unfortunately. We had a really pretty trash can that we really all admired. It looked really good. We also introduced volume profiles for improvements. So obviously, when you're working on mobile, there's a wide range of device tiers from low to high, mid, and everything in between all of that. So we developed high and low profiles to make sure we're maintaining visual quality on both a high-end device and a low-tier phone, and making sure that the discrepancies between those two isn't too severe. Also, light map baking. God, this one took, I want to say, about 30 seconds. I mean, it took us some time to sort out the lights and the new systems and all that, but once we were happy with the lights, just hit bake. Took 10 seconds. If we weren't happy in the end, a week later, our art director just came in and hit bake 3 or 4 more times, and it took him less than 5 minutes to just get the lighting sorted out however he liked it.
Once we had all of our features from the original content pipeline implemented in URP, we took a look at the shader size. Our old pipeline handled how shaders get included in build a little bit differently than in URP. So we found that our main shader, our Scopely PBR shader, was 29 megabytes, but through optimization, we reduced that all the way down to 5.4 megabytes. We use asset bundles for a majority of our assets. So we place shaders that are used across multiple asset bundles in a separate asset bundle so that they can recognize that as a dependency and the shader doesn't get included multiple times across asset bundles and duplicated in memory, because that's not what we want. In our original content pipeline, the merging process generated shader variants as individual shader files and placed those in a folder. So for that, all we had to do was include the folder in our asset bundle, and we had all of our needed variants included. URP handles this a little bit differently. So we had to use a shader variant collection to specify which variants we actually wanted included in the build. In the graphics settings menu, shown in the image, there's shader stripping settings that affect which variants get included in build. So for our light map, we use the baked non-directional and shadow mask lighting modes for all of our combat scenes. So we have both of those variants checked, the baked non-directional and the baked shadow mask. Initially, we didn't have the baked shadow mask selected, so our shadows didn't show up correctly on device. Even though we had the correct variants in the shader variant collection, we could see the keywords there. They were getting stripped from the build because we didn't have this setting checked. Once we checked it, then it showed up on build and everything was great. Both of the light map and the fog shader stripping settings have an automatic and custom mode. The automatic mode works well if you don't really use asset bundles and you include all of your scenes in build, then it'll automatically detect the variants that are used in the scenes included in build. But if you use asset bundles or load any shaders at runtime that aren't included in a scene, you're going to want to use the custom mode to make sure that those variants don't accidentally get stripped from build. So initially we used all 3 of the fog modes, but we found that this was a huge contributor to our total shader size. But we primarily used the linear fog mode. So Chris was able to go back and refactor our combat scenes. We had just a few that used the other 2 modes. Refactored those to use linear, still had great visual quality, and we reduced our total shader size by about 1/3. In addition, the URP asset has a lot of features that you can toggle at runtime such as reflection probe blending, other things like that. And so we disabled all the features that we don't use. We don't use reflection probe blending or box projection, anything like that. So we disabled those features to get those variants stripped from the build. But that didn't reduce the shader size as much as we wanted. We knew that some variants were still getting included that we weren't using. So a lot of those features in the lit and complex lit shaders are implemented using multi-compile shader directives, which generate a large number of variants. We don't toggle any of these features at runtime, and for the features that we don't use, we don't need to include these variants in build. So we changed a lot of the multi-compile shader directives to shader feature shader directives. So this prevented all of those unused variants from being included in build and just included the specific variants that we specified in the shader variant collection. In addition, we refactored our contact shadow implementation to use a custom render pass. And so for that, we were able to get all of the contact shadows for all characters in a combat to draw in a single draw call. In our previous pipeline, each of the contact shadows was a different draw call, so hip, right foot, left foot. So we reduced it for a standard 5v5 combat. There were approximately 33 draw calls to render the hip and feet shadows, and we reduced that to a single draw call. Another difference in URP is how camera stacking works. We implemented a camera stack manager to support camera stacking with additively loaded scenes. We identified and addressed excessive overdraw. We use additively loaded scenes for a lot of our UI screens. So we updated all the cameras in game to have the correct render type and added a script that registers it with the camera stack manager, and that handles sorting it properly into the active camera stack. And while we were implementing these changes, we realized that our main menu had excessive overdraw. We were drawing two backgrounds on top of each other, full screen opaque backgrounds, which we just didn't need to do. So when we were refactoring this, we made sure to disable the camera rendering the hidden background, so we were just rendering the one background. After the implementation was complete, we needed to get this update out to players and transition the rest of our team to the new content pipeline. So our main goals for release were to achieve visual parity while maintaining performance. Our primary performance benchmarks are FPS and memory usage. We utilized our quality assurance team as well as Unity's profiling tools to analyze performance and identify issues. We compared these benchmarks between the URP development build and the live build to identify any issues. We decided to go with a split release for releasing URP. This was a massive update to almost all of our assets in game. Anything we missed would show up pink and require a client update. So we coordinated the release so it wouldn't conflict with any major features in development because they were still developing in our old content pipeline. So we had to finish converting anything that they were creating to URP in order to get it out in that same release. And we aim to get this out as smoothly as possible for both our players and our development team. So for the split release, we rolled out the first release with the original content pipeline, and then we did a point release with the URP update. And this allowed us to roll out the release slower. We were able to check for issues and monitor how it was doing live. And if anything really catastrophic happened, we were able to roll back players to a stable build while we investigated the issue. The switch to URP drastically changed our content pipeline. We no longer have to manage two versions of the assets. Artists no longer have to edit a source asset, go through a merge process, and then run the game to check their fixes, and do that every time they make a change. The new content pipeline is simpler, easier to manage, and reduces artist iteration time. So after the initial update was released and any major issues were addressed, we merged our URP changes to the main development branch and transitioned the rest of the team to our new content pipeline.
And here is just a before screenshot of what we were working with. Looks okay, but it could be a lot better. And also, this is the game view that you're seeing. The scene view looked crazy and chaotic. I don't even want to show it to you. Honestly, I didn't put it in. But this is the after. So we went a little crazy with the bloom in particular. We have toned it down since. But you can see the quality of the lighting is just significantly improved. The characters actually pop out. And this is thanks to some of those improvements we added, like post-conversion, post-everything. Now we just got to the polish phase of everything. It's all real-time lighting. Well, it's mixed lighting, but it's using two real-time lights, two directional lights, one dedicated just for the environment, and then another dedicated for just the characters to help them pop. In addition, they have their own kind of post-process settings that helps both of them pop individually as well, both environment and characters. And it's just, it allows us to really immerse the characters in a way we haven't really been able to do before. Previously, you kind of were stuck with one directional light, and that was the light that they used for all the characters. So if you didn't want your characters to necessarily reflect the grounds, they were unfortunately going to reflect whatever the sun color was. Here you can see an example of this, just going back and forth between these two. They do have a dedicated sun that's kind of on the bright yellow side, but they also have a slight orange light that's kind of shining underneath them as well. That helps us immerse these characters a little bit better. In our previous engine, this particular environment was always notorious for being way too blown out. The characters just look too oversaturated and, well, overblown, really. And here, it's not really the case anymore. There, you can actually see a lot of the detail that we weren't able to see before, and that's thanks to having like dedicated lights and post-process controls that or the URP actually allowed us to have for that. Similar thing here. Again, just having those custom lights really has helped us with immersing those characters in those environments. A new process for reflection probes as well and blending and all that just gave us a whole new lease on life for this game.
So we learned a lot through this process. It's definitely important to evaluate your project and identify the benefits URP can provide. We recommend thoroughly auditing your project to gain a clear understanding of what needs to be migrated to URP and what tech debt might need to be addressed. During later stages of the migration, we encountered a few assets and shaders we initially thought were unused, and then we had to investigate and migrate those as needed. So this did add a little bit to the total time required for migration. And then we also prioritized tech debt that affected game performance. So we optimized a few VFX assets that were just spawning way too many particles, just got missed at some point. So we fixed those up so that they weren't generating a massive amount of particles. But identifying these needs early on will help with planning and execution. URP has some, or Unity has some URP migration tools. So it's important to take advantage of those if they work with your project. If you use like a lot of the built-in shaders, use a lot more of that functionality, they'll work a lot better. If not, we recommend creating custom asset conversion tools like we did. Without these tools, I don't think it would have been feasible for us to migrate our entire project. It takes significant time and effort to do this migration. With Chris and I as the primary developers on this migration, it took us about a year and a half. Our original content pipeline had a lot of custom functionality implemented in conjunction with built-in. So if your project is closer to built-in, uses more of the standard features, then it'll probably take a lot less time for yours. But overall, URP is the best long-term option for Marvel Strike Force. Our original content pipeline prevented us from efficiently creating new content, and there was no feasible way to update this pipeline and all of the existing assets.
Yeah, our pipeline has significantly improved. Again, our iteration time is just way down. We're able to just make content much faster than we used to be able to. Our artists are much happier as well with this new implementation, this new pipeline that we've put for them. They're now in more creative control over their assets. They're getting more true to their author of the original intent when they go into the engine and integrate their assets. Another one, like Emily said, an unplanned benefit for us was that we actually had to take a look at all of our old assets across the entire project's history. And there's some old jank in there. When we were converting, we said, you know, there's all of these disabled game objects. These emitters aren't efficient. We can just delete a bunch of old stuff, that just old tech debt, and we could take care of it now. We'll get the benefits of URP, that nice performance boost that we saw, plus our old assets are now optimized. So it really forced us to kind of go back and refine our old pipeline as well.
We also were able to reduce our shader complexity significantly when migrating to URP. Our original pipeline wasn't really maintained, so it had a lot of tech debt built up. Our Uber PBR shader in the previous pipeline supported a ton of features, most of which we didn't even use. So there were just a ton of shader features and keywords, which made it super hard to even read through the shader and figure out what was going on, let alone try to add new features without breaking something down one of the paths. You know, if you declare a variable and then you go down the wrong shader path, sometimes you'd get an undeclared variable error, which was not great for trying to add new features. But in URP, our custom shaders are simpler, have better structure, and are easier to update. In addition, we get improved debug tools. So our original pipeline did have a similar rendering debugger to Unity's rendering debugger, but it wasn't as effective, and it was something that we had to maintain every time we added new features. But now, since we have our custom shaders are built off of the Unity lit shader, it works with that rendering debugger already. And then the frame debugger also worked in our old pipeline, so you were still able to step through and see all of the draw calls and everything like that. But all of the renders were grouped under a custom render, so it was difficult to see which camera was rendering what and made it a little bit harder to figure out where the issue was. But in URP, all of our cameras are really clearly labeled along with all the passes, so we can really easily see the shadow pass, we can see our custom warp pass, we can see the gradient pass, and we don't have to search through it a bunch. Thank you.